Yeah, can you see the screen?
Yeah.
All right.
Yes.
Now let's just use a simple regression model to explain the dummy variables. Okay. Let's just regress wage on married. Okay. So we have a simple regression model where wage is the dependent and the marriage is the independent. Okay. Now we will see the coefficient to what 178 point something. So and the sign here is positive. What this means is that those who are married will earn 178 Ghana cedis higher than those who are not married. Are we together? Those who are married will earn 178 Ghana cedis higher than those who are not married. I was trying to tell you that we can change it and tell Stata that he should change the reference dummy. We don't want to use those who are married as a reference. We want to use those who are not married. There's a command that we can use to swap it. The command is xi column regress with 0 married. Since 0 means those who are not married. When you regress this, you see that the sign has changed, but the coefficient didn't change at all. When those who are married was the reference dummy, we had positive 178.6079. When we change it to those who are not married, the coefficient changed to minus 178.6079. So if this is what you have, now those who are not married is a reference dummy. So you say that those who are not married will earn 178 Ghana cedis lower than or less than those who are married. You understand? You see that the meaning is the same thing, but the references are different. If the person is married, the person is getting 178 more than the person who is not married. And then if the person is not married, the person is getting 178 less than those that are married. Is that okay?
Yes, but say what command did you use? Did you use SI?
Yes, XI, let's
Yeah.
use. Then
It's saying that SI is an unrecognized command.
did you just type XI? Did you take the column?
Yes, I did.
You did there.
Yes.
Which Stata are you using? Is Stata what? Did you install Stata small?
Yes.
I don't. You see that when you do something in Stata and then you get an error, there's some R there. You can follow it and then they will tell you the reason why you are getting an error. Did you see the?
Yeah, I did.
So you can just follow that link and then they'll tell you why you are having an issue with that command. But unless, of course, after school you'll be doing research, you don't need it because they will not come and tell you to go and do it. They will rather do it and then bring you the output. But in case you are interested in using these things after school, then you have to know all these commands. Okay. But please, I hope we understand the interpretation of the dummy variables.
Yes.
Okay. Now, let's go back to the multiple regression model. Now, we want to look at test of significance. Okay. Test of significance, individual significance. Now, we have regressed or we have a model where these independent variables, hours of work, age, and then married are trying to determine the wage of a particular worker. Okay. Now the question is that, is age significant? Does age actually cause differences in the workers' wage? If you take any two distinct workers, can their age actually cause a difference between the wages that they receive? That's what the significance is all about. So if you get an independent variable to be significant, then it means that if you come to the real world, yes, age can actually cause a difference between the wages for two distinct workers. If we take married, and is significant, it means that there is actually a difference between the wages of those who are married and then those who are not married. Okay, so that is the test of significance. If you have the output like this, we have two ways of doing that. In other words, and when you are testing for significance, the null hypothesis is that that value is equal to 0. That variable is equal to 0. If the variable is equal to 0, it means that it doesn't have any significant impact on the dependent variable. And then the alternative is that it is not equal to 0. So if we reject HO, then it means that the variable is statistically significant and it impacts a significant effect on dependent. But if we fail to reject HO, then it means that there is no statistical significance. In other words, that variable doesn't exert any significant impact on the dependent variable. So the test of significance here, we are testing. That's from the regression output like this. It's two-tailed. The null hypothesis is that the beta is equal to 0. And then the alternate is that the beta is not equal to 0. So how do we test that? First, we can use the confidence interval. We can use the confidence interval. If beta is equal to 0, okay? If beta, we want to see if beta can actually be 0. We can only have a 0 number between two opposing numbers. Before we can have 0 within an interval, one number must be negative and then one number must be positive. Are we together?
Yes.
0 can never fall within two positive numbers or two negative numbers. And the confidence interval, of course, by the name is an interval. So if you take hours of work, the first interval, how do we it upper limit? Or the first number is negative. The second one is what? Is positive. If you have one positive, one negative, then it's possible that that variable can be 0. Are we together?
Yes.
So if you take the confidence interval and one is negative, one is positive, you fail to reject HO. What it means is that that variable is not statistically significant. So beta 0 can indeed be equal to 0. So one, we can use the confidence interval. When the signs are different, we fail to reject HO. Let's take age. If you take age, the two bands are all what? Are all positive. And 0 cannot fall within a positive number. So for age, we reject the null hypothesis that age is equal to 0. So if we are rejecting the null hypothesis that age is equal to 0, then it means that age is not equal to 0. So age actually has a significant impact on the wage of the worker. And because the sign is positive, it means that the higher your age, the higher the wage that you actually receive. But for hours of work, we can't actually say that when it comes to the real world, the number of hours that the person works actually affects the person's wage. It doesn't. It doesn't affect the person's wage. Okay. If you take marriage too, you see that we have two positive numbers. Okay. So this means that we reject the null hypothesis. Married cannot be 0. So married actually exerts significant impact on the person's wage. So because the sign is positive, if you want to earn higher wage, if you want to increase your wage from whichever level by 150, now you have to get married, because those who get married earn higher wage than those who are not married. So you can use the confidence interval to test for the significance, to test for whether that variable is significant or not. Okay, so that is one thing that you can use. Or you can use the p-value. You can use the p-value. Here, the decision rule is that if the p-value is smaller than the significance level, reject the null hypothesis. If the p-value is less than the significance level, you reject the null hypothesis. Now, the confidence interval is 95. So the significance level is 5%, 0.05. So if you take the first one, the p-value for hours of work is 0.596, which is greater than the significance level of 0.05. So we fail to reject the null hypothesis. The decision rule is that reject the null hypothesis if the p-value is less than the significance level. Here, the significance level is 5%. So the p-value is 0.596. It's greater than the significance level of 0.05. So we fail to reject the null hypothesis and state that hours of work doesn't have any significant impact on wage. And you see that you get the same decision as when you use the confidence interval. One is negative, one is positive. So we fail to reject A2. P-value is greater than the significance level. So we fail to reject A2. Are we together? Hello.
Hello.
Yes.
Okay. Then let's look at married. The p-value for marriage is 0.000. And 0.000 is less than 0.05. So what is the decision here? We reject the null hypothesis. Okay, since the p-value is less than the significance level. So as we are rejecting the null hypothesis, it means that age actually is statistically significant. That when we use a confidence interval too, that's the same thing that we had. If you take married, okay, if you take married, here married is 0.000. So if the p-value is less than the significance level, then yes, we reject the null hypothesis and state that married is actually statistically significant. And when we use the confidence interval, we have the same. I hope we.
Yes.
You can choose to use your the mechanical way. You compare your T stars to the T
critical.
Yes, you take the critical value. So here, if you want to do that, you need to know the degrees of freedom. So you go and read it from the T table, then you come and compare them. Okay, you come and compare them, but that will just be a waste of time. You can just use a p-value. So you just use a p-value. You can just use a confidence interval. So what we are doing is t-test, individual t-test. So we are doing it for the individual variables. What about the joint test, the F test? Okay, that one we are doing joint significance. I mean, what this means is that is the whole model significant when we take these independent variables jointly, do they actually have any significant impact on wage? That is what we use the F test for. That one will come here. Here too, we can use the F stars. The F statistic here is 12.72. Then you go and find your F critical. Then you compare them. Or we can use probability greater than F, probability greater than F for the joint significance. Here, the decision rule is they say if the probability greater than F is less than the significance level, then you reject. Here, the null hypothesis is that all the variables are equal to 0. Jointly, they don't exert any significant impact. So they are all equal to 0. So the null hypothesis will be stated as beta 1 is equal to beta 2 is equal to beta n, all equal to what? 0. I'm sure you've seen that test before. All the parameters are equal to 0. That's a joint test. That jointly the independent variables will have no significant impact on the dependent variable. Then the alternative will be they are all not equal to 0. Okay. So now if you come here, use a probability greater than F. It's 0.000. It's less than the significance level of 0.05. So we reject the null hypothesis and state that jointly the independent variables will have a significant impact on the dependent variable. Is that okay?
Yeah.
Okay. Then this is the R squared. I'm sure we all remember how to interpret that. It measures the percentage of the variation in the dependent that can be explained by the independent. Okay, so here this will be, if you convert this to percentage, you get what? Is it 3.6%? So
3.94%.
0.3, so 3.94%. See that it's the model isn't very efficient. Just less than 4%. Less than 4% of the changes in wage can be attributed to the differences in hours of work, age, and then marriage. You see, it is not good at all. Okay, it's not good at all. So this is how we get our. I'm sure you've understood the interpretation.
Yeah.
Now, you can also do your T test, the individual T test. Apart from using the table like this, the command is T test. T test. Then whichever variable that you want to use, if it's age, you want to T test age. You just type T test age. You've I'm coming. T test age equals 0. What am I typing? So we want to test that age is equal to 0. So the null hypothesis is that see, this is where the null hypothesis is. You see, the mean is equal to 0. Okay, so the mean of age is actually equal to 0. Now, that is the null hypothesis that you told Stata. So the alternative is that age is not equal to 0. If you look at this, this is the T stars. Okay, this is the T stars. So you can compare this to the T critical. You've been given the degree of freedom as 924. Okay, so you can do this, use the old crude way, and then you test for the significance, or you can use the values. Okay, here you see that when you are doing hypothesis testing, you can have left tail, right tail, or two-tailed. Okay, two-tailed. That one depends on the alternative hypothesis. If the alternative now is that age is equal to 0, so the alternative can be age is less than 0. That is the left tail, or the alternative can be age is not equal to 0, two-tailed, or age is greater than 0, right-tailed. Okay, so it depends on the alternative that you are going for. It doesn't matter which one you are going for. We still use the p-value. So assuming the alternative hypothesis is that the mean of age is less than 0, then this is the p-value. The p-value is 1. 1 is greater than 0.05. So we fail to reject the decision rule is the same. If the p-value is less than the significance level, you reject the null hypothesis. You fail to reject if otherwise. So here for alternative being mean less than 0, the p-value is 1. So if the p-value is 1, then we fail to reject the null hypothesis. What this means is that the mean cannot be negative, cannot be less than 0. If you come to the right tailed, mean is greater than 0. You see that the p-value is 0.00. This is less than the significance. So we reject the null hypothesis and accept the alternative hypothesis. If you come to this one too, this is the two-tailed. So mean is not equal to 0. So if it's not equal to 0, see that the p-value is 0.00. So we reject the null hypothesis that age is equal to 0 and accept that the mean of age is not equal to 0. Is that okay?
Yes.
Good. Now, I'm sure you've seen questions where you were supposed to test that maybe beta 2 is equal to beta 1. Have you seen something like that? That is where you
Yes.
use the variance covariance matrix to find the standard error for beta 1 minus beta 2. I'm sure you've done something like that.
Yeah.
Yes, yes.
So that one too, we can use t-test. Assuming we want to test that the mean of age is equal to the mean of married, okay, or hours of work. So age is equal to hours of work. Okay, so here we are testing that, and the null hypothesis is that there is no difference in their means. So beta 1 minus beta 2 is equal to 0. That is the null hypothesis. Okay, they are the same. Beta 1 is equal to beta 2, or beta 1 minus beta 2. Beta 1 minus beta 2 is equal to 0. Then the alternative, we can have all the alternatives. This one, the first one, the alternative is that the difference in means is less than 0. Okay, it's less than 0. So you use your decision rule here, we reject the null hypothesis. Then this is the two-tailed, that is exactly equal to 0. We reject the null hypothesis. But here is greater than 0. We fail to reject the null hypothesis. Okay, we fail to reject the null hypothesis. So here the difference in means cannot be greater than 0. Is that okay?
Yes.
Okay. And then the joint test too. The joint test. I think that one we can use test, assuming after running your regression. Let me check something. This one too is the F test. The F that we have here, okay, this F test here is testing for the significance of all the independent variables here. What if we just want to test that beta 1 is equal to beta 2 is equal to 0? See, the last one that we did here was beta 1 is equal to beta 2. You understand? Beta 1 is equal to beta 2, but we can be asked to test for beta 1 being equal to beta 2 being equal to 0. What it means is that jointly they are all equal to 0. But the t-test on, it means that the two are the same. Are we together? Like, do we see the difference? This mouse, I don't know what is wrong with this mouse. The first one that we did was maybe beta 1 is equal to beta 2. Okay, so if beta 1 is equal to beta 2, it means that there's no difference between the two betas. But the F test that I'm talking about now is beta 1 equals beta 2 equals 0. This is different from this. Okay, what this is trying to say is that jointly these two variables are all equal to what? Equal to 0. So if we have this number of independent variables, then this is how this test will be like. Like jointly, all the variables that we are using are all equal to 0. We can do that. If you do that, you see that you get exactly what Stata reported from the regression model. Here, we had F stars to be 10.04 because we used only age and then hours of work. But if we have to use all, okay, if we have to use all, we are testing for hours, we are testing for age, and then married. See, from the regression model, you see that we had 12.72. And then from this F test to the F stars is what? 12.72. So this is the test that Stata reports as part of the regression model. Okay, so in case you are asked to test for the joint significance of some particular variables, it's just the command is test. Then you just add whichever variables that you want to test. Okay, whichever variables that you want to test. So that is about the hypothesis test. Please, any question? Any question? Then we have to look at the residuals and then the predicted values. I'm sure you remember from the stars that after you've gotten your regression line, you can find the fitted values, the y hat, okay, the predicted ones. We have y hat, and then we have the residuals, okay. Now we have been given a value of wage here. We have run a regression model. We want to use the model to predict the wage. That's what we call the predicted y, or the fitted y, or the y hat. But then it's more like, because the model is not perfect, there'll be a difference between the predicted value and then the actual value. The difference between the two is what we call the residuals. Okay, I'm sure you guys will remember that. So please, let's go back and do the regression again. Let's regress this. Regress wage on hours of work, age, and then marriage. Now we want to find the predicted values for wage. Now we have a model. In case I didn't tell you that initially, I told you that most of the times the first thing you have to do is to report the model. So wage is equal to the constant will come, then the coefficient for hours times hours, and then all that. So after that, you can be given an example, like if the person is 20 years old. Now we can say a married worker is 25 years old and works for 10 hours per week. What will be the person's wage? So after you have reported the model, wherever you see married, you put 1, because we are saying that the person is what? Is married. So this is how you do it. You write this. You write wage into brackets. This mouse. You can write your wage, just write your full wage. Then you do this wage, then you bring this bar, okay. Hours of work is equal to 10, comma, age is equal to, I said 25 years, and then comma, for married, the person is married, so that is equal to 1. Then you go to your model. The constant comes first. Then hours of work is minus 0.9 something times whatever hours, so times 10. Then you go to age, it's 18 point something times the person's age is what? 25. Then you go to the person is married, so it's just substitution. You put in the information, then you are able to get the wage for that particular person. Of course, that's what we use regression for, to predict. Okay, we use a regression to do prediction. So after getting this model, how do we get the predicted values? Okay, when you take the model and you substitute whatever values of the independent variables, how do we get the fitted values, or the y hat? So here the wage hat. So we use the command predict. Okay, so go to the command window, type predict. Then whatever name that you want to use then the name that you want to give to the y hat, you can use wage hat or predicted wage, or whichever name that you want to use. I'm using wage hat. Okay, so predict wage hat. Okay, then enter. Predict wage hat and enter. So now if you go to the variable window, you will see that there's a new variable called wage hat. There will be a new variable called wage hat. So that will be the fitted values from the model. Okay, we'll browse it and see. Okay, we'll browse it and see. But let's look at the residual tool. For residual tool, the command is still predict. Then maybe let's use residual wage. So the residual for wage, comma, then you add residuals. Okay, so predict the name you want to use for the residual, then comma, residuals. Okay, predict the name, comma, then residuals, then you enter. If you go back to the variable window, you will see a new variable there as well, receipt wage. Okay, receipt wage. Now let's browse wage. Okay, let's browse wage, then the wage hat, and then the receipt wage. Browse wage, wage hat, and then receipt wage. Oh, the thing is browsed. I added W. Okay, so if you did it well, this is what you are supposed to get. The actual value of wage is 769. The predicted wage from the model is 939.7151. The residual is minus 170. So you see that there's a difference between the predicted wage and then the actual wage. If you add the wage hat and then the residual, you get the actual wage. Okay, if you take this, you can use your calculator, add this to this, you come and get this. Okay, so whenever you add the predicted value to the residuals, you are supposed to get the actual value. Okay, get the actual value. Okay, so it's just a command that you need to know. Predict, then whatever name you want to use for the predicted, then predict the residual name, comma, residuals. That will give you the error terms. All right, I hope we understand this one as well. All right. Have you been taught the log transformations? Hello.
Yes, we've done, but I haven't gone through.
Okay, so the regression that we did here is linear. The dependent variable is linear. The independent variable is also linear. So we call it linear. But we have log transformations, and that gives rise to log linear regression models, linear log models, and log models. As soon as we transform them, the interpretations are different. As we transform them, interpretations are different. Please, let's be very attentive to this one because it comes a lot. On the examination paper, you see that they will have logged values. The interpretations will be different from the linear ones. Okay. So let's transform. Let's just use a simple regression model. Okay. Let's use wage, and then you cannot log a dummy variable. We don't log dummy variables. Let's take wage and then hours of work. Okay, let's take wage and hours of work. So I'm sure you remember how to generate new variables. Let's generate a variable called log wage. Okay, where log wage is equal to the log of wage. Okay, the log of wage. So generate log wage equals log wage. You put in that. Now, if you go to the variable window, you see a new variable called log wage. That is the log of wage. Then let's also generate a new variable called log hours. And this is equal to the log of hours. So this one, to go to the variables window and you see log hours there. Okay, log hours. Now, let's run a log simple regression model on wage and hours of work. Please, the meeting will go off. You have to reconnect again. We have to finish. There is no time. So regress log wage on log hours. Regress log wage. Please, let's do the linear so that we can compare them. So regress wage on hours, linear, wage on hours. So that is the regression model that we have here. Now let's regress log wage and then log hours. I want us to compare the two. The hours it's not proper. Okay, let's look at this now. The first one is linear. So when you are giving the interpretation, you interpret them in terms of units. So here we say that if hours of work should increase by 1 unit, then wage will decrease by 0.5 units. Linear, we talk about them in terms of what? In terms of units. As soon as you log them, we talk about them in terms of percentages. Okay, we talk about them in terms of percentages. So here, wage has been logged. So the change in wage must be in percentage terms. Then hours of work too is logged. So the change in hours of work must also be in terms of what? Percentages. Is that okay? Are we together?
Yeah. Yes, please.
Good. Now, let's do log linear. Okay, I want us to have all the models before we do the interpretation. Now, if you compare the linear to the log, you see that here the coefficient is 0.10, but here the coefficient is 0.5. You see that there's a difference, right? Now let's look at log linear. Now you see what we have here, minus 0.00. You see, it's quite different from the log. Then let's look at the last one, linear log. So wages rather linear, and then this one is log. You see how the thing is. Very good. Please, are we together? Have you stopped doing it on your laptop? You have stopped, right?
They are doing
You are-
no. Yes.
So please, do we all have these models on our laptops?
So I was writing the commands in this one, do file. So I'm now doing.
The previous ones that we did I send you the do file?
No.
Oh, all right, don't worry. I'll add this one and then send them to you. All right, this meeting is almost over, so when it goes off, then you will connect it and then you give the interpretation.